Welcome to the deep dive. You know, most architectural documents can be, well, a bit dry, blueprints.
Right.
But today, we're diving into something really ambitious. We're looking at a plan from a single developer, believe it or not, to build what they're calling a six-platform powerhouse.
That's right, and we're going to dissect the full-stack architecture behind it. It's a real-time, high-volume file-sharing app.
And the kicker is, it's designed to run natively from just one code base. Think Android, iOS, Windows, Linux, macOS, and web.
Yeah, it's really an exercise in getting maximum platform reach with, ideally, minimum development headaches.
Right.
That's the goal anyway.
And our listener shared these detailed source documents because the app itself tackles a massive pain point. I mean, we've all felt this, right?
Yeah.
Cloud storage is everywhere. But if you just need local, fast file transfer, say, moving a big presentation from your Mac to a Windows machine right next to it.
It's often awful, laggy, unreliable. You end up emailing it to yourself or using a USB stick.
Exactly. And this application, well, it specifically engineers its way around that whole problem. The entire system is kind of built around using persistent WebSockets. The idea is to get that near-instant local-like file transfer feel, even if the devices aren't physically close.
Okay, so our mission today is basically a full architectural X-ray. We need to unpack every key decision here.
Right, from the Flutter choice on the front end,
Through scaling Node.js with clusters.
all the way to using GCP's Gemma AI model for some clever features.
Yeah, and we're really looking at the plan for scaling this. How do you take it from a smart proof of concept to something that can handle potentially millions of users?
It's all about clean architecture, thinking about distributed systems from the get-go.
So by the end of this deep dive, you should have a pretty complete blueprint for how these modern high-performance cross-platform systems get engineered today. Thinking about efficiency, thinking about scale.
Absolutely. Let's get into it.
Okay, let's start right where the user touches the system. The front end. The sources make it super clear. Flutter was the foundation.
Given they're targeting 6 different platforms, why was Flutter such an undisputed choice here? Seems daunting.
Well, the main driver was really development velocity, pure efficiency.
Okay.
Choosing Flutter meant committing to one single code base that then compiles natively for all 6 targets. Imagine trying to manage 6 separate stacks: Swift, Kotlin, C#, maybe React for web.
Right, it'd be a nightmare. Probably kill the project before it even got off the ground.
Exactly. Flutter lets them maximize that platform reach while drastically cutting down the maintenance burden.
But, okay, an app this big, spanning so many OSs, complexity must just explode, right?
Oh, absolutely.
And the source material really hammers this point. Clean architecture wasn't just a nice to have, it was non-negotiable.
Totally non-negotiable. When you need portability and maintainability like this, clean architecture is, well, essential. It forces a really strict discipline on you.
How so?
You have to separate your code into distinct layers. There's the data layer. That's where you talk to external APIs, databases, all that stuff. Then the domain layer. This is a pure core business logic. The rules of your app. No dependencies on UI or databases here.
The brains of the operation, basically.
Exactly. And finally, the presentation layer, which is the UI itself, what the user sees and interacts with.
So what's the real payoff? For the developer, or even for the user down the line, why enforce that strict separation?
Flexibility is the big win. Let's say next year the team decides Flutter isn't the future. They want to use, I don't know, compose multi-platform.
Right.
With clean architecture, they only need to rewrite the presentation layer, the domain layer, all the core logic about how files are handled, shared, tracked, stays completely untouched.
Ah, I see. So you isolate the valuable business logic from whatever UI tech is trendy this year.
Precisely. It protects your core investment.
Now, state management. That's always tricky, especially in a real-time system tracking uploads and connections across, again, 6 platforms. They chose BLOSC business logic component. Sounds complex. Reactive programming stuff.
It is a bit complex, but it's powerful.
Yeah.
What's really interesting here is how BLOS helps manage that complexity and maintain stability across all those targets.
How does it do that?
Instead of having bits of logic scattered all over your UI code, you isolate major features into their own blocks. Think of a file transfer block or a connection status block.
Okay, so each feature gets its own little manager.
Sort of, yeah. And it works using streams, reactive streams. The UI sends a stream of events into the BLOS.
Like user tapped upload button.
Exactly. Or upload file X. The VLC processes that event, does its logic, maybe talks to the data layer, and then it emits a stream of states back out to the UI.
States like uploading 10%, uploading 50%, upload complete.
Precisely. And the real genius there, like you said earlier about clean architecture, is that the UI code becomes incredibly simple, almost dumb.
How so?
It's purely declarative.
Yeah.
It just sits there waiting to receive a new state from the VLC stream, and when it gets one, it just renders it instantly.
So it doesn't need to constantly ask, hey, what's the status now, or figure out how the state changed.
Nope. It just knows what the new state is. And that's crucial for making sure that file upload progress bar ticks up smoothly and reflects what's really happening, giving you that seamless feel on your Android phone, your Windows desktop, everywhere.
All right, that makes sense. Let's move deeper into the stack, the backend engine, the real-time part. They picked Node.js and Express.js. Now, Node is famous for speed, non-blocking I/O. But it also has that, single-threaded limitation. For something doing high concurrency file transfers, wasn't choosing Node a bit of a gamble? Maybe Go or Rust would seem more obvious.
That's a really critical question. And yeah, they definitely sacrifice some raw CPU crunching power compared to Go, no doubt.
So why Node?
Development velocity, again, and the massive Node ecosystem.
Right.
But the key technical reason is that non-blocking I/O model you mentioned.
Yeah.
Node isn't the fastest processor, but it's absolutely superb at handling thousands of simultaneous connections that are mostly just waiting for network data, waiting for file reads.
So it's great at juggling lots of slow things.
Exactly. Which makes it perfect for I/O-heavy tasks like managing tons of WebSocket connections and shuffling file data around. They traded a bit of raw speed for huge flexibility and, frankly, getting the thing built faster.
And for those file transfers, up to 250 megs according to the docs, they went all in on WebSockets. No traditional HTTP requests for the actual transfer.
Yeah, that was pretty much non-negotiable for efficiency. If you're sending a big file, you really need that full duplex persistent connection.
Like keeping a phone line open instead of hanging up and redialing constantly.
Perfect analogy. WebSockets establish one connection that stays open, minimizing all the network chatter and latency you get trying to chunk a large file over standard HTTP requests. It's just way more efficient for this use case.
But we still have that core node challenge, the single thread. How did they tackle that immediate capacity problem without switching languages?
They used a really powerful built-in node feature, the cluster module. This is their first line of defense for horizontal scaling.
Okay, what does that do?
Instead of just running one node process, the cluster module lets a single master process fork several identical worker processes.
So if the server has, say, 8 CPU cores, you can run 8 separate node instances, all listening on the same port.
Exactly that. You immediately leverage all the available CPU power on that single machine.
Okay, that makes a huge difference.
It instantly boosts your overall throughput and availability. Plus, if one worker process happens to crash for some reason, the master could just spawn a new one, the service stays up. Anyone who's wrestled with node crashing under load knows how vital this is.
Okay, the cluster module is smart for maximizing one box. But yeah, that box still has limits. We'll definitely circle back to the ultimate scaling challenge later. Quick question on data persistence first. MongoDB.
Right. User profiles, file metadata like summaries, we'll talk about connection logs. All of that non-file stuff goes into MongoDB.
Wow, Mongo.
It's a document database, so it offers schema flexibility, which is handy when things are evolving. And it generally has good write performance and stability, which you need when you're constantly logging dynamic connection states in a real-time system.
Makes sense. Okay, let's shift gears now. Cloud strategy and that AI future. The sources lay out a pretty pragmatic approach, kind of dual cloud, focused on cost and starts.
Yeah, it's a clever split, actually. For the actual user files, the heavy lifting, the terabytes of storage that goes to Backblaze B2.
Why Backblaze?
Cost. Simple as that. Backblaze B2 offers incredibly cheap, scalable object storage. It keeps the biggest potential operational cost storage way down.
But the intelligence, the brains, that lives over on Google Cloud Platform GCP. Why the split? Why bring GCP into it just for that?
Because GCP is where they access specialized high-impact services, specifically Vertex AI and the Gemma model.
Ah, the AI piece.
Right. This powers what's probably their standout feature, AI-powered text summarization of uploaded documents.
All right, that sounds cool. How does that work?
It basically transforms their cloud storage from just a place to dump files into a searchable smart library.
But why use a big language model like Gemma for summarization? Couldn't they use simpler text processing libraries? Cheaper, maybe?
They could for simple stuff, but Gemma earns its keep, so to speak, with complex, unstructured documents. Think about long annual reports, dense research papers, meeting transcripts.
Right, stuff that's hard to get the gist of quickly.
Exactly. Gemma doesn't just pull out key words. It can actually understand nuance, context, and generate a concise, coherent summary that a basic algorithm just couldn't manage. It turns a 100-page document into something you can grasp in seconds.
That is powerful. Okay, let's trace the workflow. How does the system even know when to ask Gemma to summarize something? It can't be doing it instantly on upload, right?
No, it's asynchronous, event-driven. It's quite elegant, actually.
Walk us through it.
Okay, so user uploads a file. Let's say it goes to Backblaze B2.
Right.
That upload action in B2 is configured to fire off a webhook.
Just a little notification.
Yeah, an HTTP call, basically, saying, hey, new file arrived.
Uh-huh.
That webhook triggers a GCP Cloud function, just a small piece of serverless code.
Okay.
That Cloud function then makes the call to the Gemma model via Vertex AI, passing it the document location. Gemma processes the document in the background.
So the user isn't waiting for this?
Not at all. Once Gemma finishes and produces the summary, the Cloud function takes that summary text and stores it back in the MongoDB database, linking it to the original file's metadata.
Nice. Very efficient. Doesn't block the main file transfer flow.
Exactly.
Yeah.
And one more thing on GCP, they've also integrated GCP loggers directly into the Flutter app itself.
For operational intelligence. Catching bugs in the wild.
Precisely. You can test all you want, but you'll never catch every weird edge case or fatal error until your app is running on thousands of different real-world devices across all 6 OSs. Centralized logging gives them instant visibility into production failures. Super important.
Definitely. Okay, let's talk about some immediate wins and the near-term roadmap. The team seemed focused on simple but high-impact UX stuff, too.
Yeah, like that QR code feature for downloading files.
Right. Instead of typing weird URLs, just scan a QR code on another device. Elegant solution to a cross-platform headache.
It's just directness over unnecessary complexity. They also tackle another common pain point, dealing with deprecated mobile deep linking stuff.
Yeah, like the old Firebase dynamic links going away. That broke things for a lot of apps.
Right, so instead of relying on third-party services that might disappear, they just built their own simple, custom server-side redirect system.
How's that work?
It just looks at the incoming request user agent string that little bit of text that says, I'm Chrome on Windows, or I'm Safari on iOS. Based on that, the server just issues the correct redirect, either to the App Store, Google Play, or maybe a fallback web page.
Simple, reliable, under their control. Smart.
That's solid engineering. Predictable.
Now, their current CI/CD setup, the way they build and test, it's deliberately lean right now. GitHub for code. Push builds to a static server for quick tests.
Makes sense for a small team or early stages.
But the source material flags a huge bottleneck currently. The backend server is running on a free instance from render.
The dreaded free tier limit.
Yeah, it apparently proved the architecture works, which is great validation, but it's hitting a hard capacity ceiling.
Absolutely. That free tier is the immediate bottleneck. Before they can even think about onboarding a significant number of users, they have to upgrade to a paid multi-core instance. That's step one.
So they can actually leverage that Node.js cluster module they built in.
Exactly. Right now, it's probably running on a single core anyway. The upgrade unlocks the clustering benefit.
And even before that paid upgrade, they've got a list of other low-cost, high-impact features lined up, stuff that doesn't require massive re-architecture yet.
Yeah, these are smart wins. Things that leverage the existing setup, like file versioning. On Backblaze B2, that's often just a configuration change in the storage bucket settings. Super cheap to implement.
Nice. What else?
They plan to add an offline mode for metadata in the Flutter app.
So you can see your file list and maybe those AI summaries even if you're offline.
Exactly. Using local database tech within Flutter, maybe something like Izer or Hive, to cache that metadata locally. Great UX improvement.
And on the server side, to keep things running smoothly on that soon-to-be-paid clustered instance.
Automated WebSocket heartbeats. This is crucial for efficiency.
Explain heartbeats. Like a pulse check.
Pretty much tiny little ping messages sent back and forth between the client and server over the WebSocket connection. If the server sends a ping and doesn't get a pong back quickly,
it knows the client disconnected. Maybe they closed their laptop or lost internet.
Exactly. It allows the server to immediately identify and prune those dead or ghost connections, which means it frees up memory and resources on the server cluster that would otherwise be wasted holding onto connections that aren't actually doing anything. Essential housekeeping.
Okay. And the last big feature on this immediate roadmap, rooms for collaboration. This sounds like it pushes WebSockets a bit harder.
Yeah, this is where simple one-to-one WebSockets start to show their limits.
How so?
Basic WebSockets are great for user A sending a file directly to user B. But in a collaborative room, you need something more. User A uploads a file, and maybe users B, C, and D all need to get notified instantly.
Right, like a chat room model.
Exactly. You need to evolve the WebSockets into a proper publish-subscribe system, or pub/sub.
Pub/sub.
Yeah. One user publishes an event, like new file uploaded, and multiple subscribers, everyone else in the room, instantly receive that update. That's the pattern you need for real-time multi-user collaboration. It's a step up from basic point-to-point WebSockets.
Got it. Okay, that leads us perfectly into the final major scaling challenge. We established the Node cluster module is great for scaling up on one machine.
Right. Immediate horizontal scaling within a single instance.
But that one machine, even a beefy paid one with multiple cores, is still ultimately a single point of failure. And it does have a capacity ceiling. What happens when you really start getting traction? Millions of users hitting that single clustered instance.
You hit the absolute limit of what we might call the clustered monolith.
Yeah.
It's still fundamentally one server, albeit a clever one. The roadmap in the sources clearly shows they know this. They've outlined the necessary steps to evolve into a truly distributed service architecture.
Okay, designed for serious resilience, serious scale. What are the steps?
There are 3 critical steps laid out. Step 1 is all about tackling the real-time state. They have to eliminate sticky sessions.
Sticky sessions, what does that mean here?
Right now, because a user's WebSocket connection is handled by one specific worker process on that one machine, the load balancer has to make sure that user always gets sent back to that same worker. That's sticky.
Ah, because only that worker knows about their connection.
Exactly. And if that specific worker process, or worse, the entire machine goes down, poof, connection lost. Yeah. Game over for that user's transfer.
So how do they fix that?
They need to implement a dedicated message broker, like Redis, specifically for handling all the WebSocket traffic and state. Redis effectively becomes the central hub for who's connected and what's happening in real time. It pulls that state out of the individual Node.js application servers.
Why is pulling the state out into Redis so fundamental?
Because it allows the Node.js application servers themselves to become stateless. They no longer need to hold on to individual connection details.
Okay. And the benefit of stateless servers is?
Now, the load balancer doesn't care which server instance handles any given request for a user. Any server can process it because the state lives centrally in Redis. The servers become interchangeable, disposable compute units.
Got it. Which perfectly sets up step 2, right?
Yeah.
Distributing the actual compute power.
Exactly. Now that servers are stateless, you can move off that single host entirely. You move into a proper cloud auto-scaling groupthink, AWS EC2 auto-scaling, or Google Compute Engine managed instance groups.
Managed by a smart load balancer.
Right. With Redis handling the state, the load balancer can automatically spin up or spin down dozens, even hundreds, of these non-sticky Node.js instances based purely on real-time demand. You get true elastic horizontal scaling. Need more power, add more servers instantly, traffic drops, scale down automatically to save costs.
Okay, that's huge. And finally, step 3. The data's got to keep up too, right? Scaling MongoDB.
Yep. Even with scalable compute, if all the servers are hammering a single database instance, that becomes the new bottleneck, especially with write-heavy operations like logging metadata for millions of uploads.
So what's the plan there?
First, for handling high-read traffic, like lots of users browsing their file lists, they'll implement MongoDB read replicas, just copies of the database optimized for fast reading.
Standard practice.
Pretty standard. But the ultimate step for truly massive scale, especially handling the write load, is planning for database sharding.
Sharding. Okay, break that down for us. What does that mean practically?
Okay, think of your current database as one enormous central library holding all the user metadata. Sharding is like saying, this library is getting too full and busy, so you decide to split it into multiple separate, smaller library buildings.
Like building A handles user accounts starting A through M. Building B handles M through Z.
Exactly like that. You partition the data based on some key, like username range or geographic region or just hashing the user ID, and distribute the data, and crucially the write load, across multiple independent database clusters. This ensures no single database cluster ever gets overwhelmed. It's how you handle truly web-scale write traffic.
Wow. Okay. So we've really covered a ton of ground today. From the smarts of Flutter with clean architecture
and BLC for state.
to squeezing performance out of Node.js with the cluster module.
Then that clever, cost-effective AI workflow using Backblaze, GCP functions, and Gemma.
And finally, laying out that clear, essential three-step roadmap to get from a clustered monolith to a truly resilient, horizontally scalable, distributed system using Redis, autoscaling, and database sharding.
Yeah, I think the main takeaway here is seeing the strategic choices and trade-offs. They prioritize getting something working quickly and across platforms using Node and Flutter.
Right, development velocity.
But they didn't ignore the future. They immediately implemented the cluster module as a first scaling step. And crucially, they have a clear, documented plan for paying the necessary architecture tax, later moving state, to Redis, distributing compute, scaling the database.
So planning for that scale early, letting the architecture guide the features, not the other way around.
That's how you build successful, scalable systems today. You have to think ahead.
Absolutely. Okay, so here's a final provocative thought for you, our listener, to chew on, based on this journey from proof of concept to potential massive platform. We saw the Node.js cluster module gave them immediate horizontal scaling on one machine. But looking at that future roadmap, which step do you think represents the true tipping point? The moment this application transitions from being just a really successful, high-performing side project into a genuinely resilient, enterprise-grade distributed platform. Is it step 1, introducing the Redis message broker to decouple state? Or is it later, step 3, when they absolutely need MongoDB sharding to handle the right load? Which one feels like a point of no return into true distributed systems territory?
Something to think about. Which change fundamentally alters the nature of the system?
Exactly. We'll leave you with that thought. Catch you next time for the next deep dive.